Alright, so in this lesson we're going to start talking about angular momentum, and this is another way to talk about rotational motion. And if we look at angular momentum, one way we can describe it is I times omega, moment of inertia times angular velocity. But there's also a way we can describe it as a cross product of radius and momentum. That r cross p, where r is the distance or the vector from the axis of rotation to the location of the particle, kind of that displacement vector, and p is the momentum vector. If we think of p in terms of mv, we can actually pull the m out and call it m r cross v if we wanted to. The thing to point out about angular momentum is that net external torque is zero, angular momentum is conserved. One of the best systems to look at conservation of angular momentum happens to be figure skating. And let's look at my figure skater right here as this figure skater kind of goes through her motion. So what's happening here is as she tucks her arms in, she's actually decreasing her moment of inertia, bringing more of her mass in toward the center of her axis of rotation. What that does is it would decrease her moment of inertia and increase her angular momentum. Or excuse me, not increase her angular momentum, increase her angular velocity. Sorry, angular momentum remained constant. So first thing I want to do is calculate the angular momentum of a system of two particles that are moving at constant momentum along horizontal paths as depicted in this picture here. Particle 1 has a momentum of 5 kilogram meters per second and is currently at a position r1 away from point O, but will pass 2 meters away from point O. So this horizontal distance here is 2 meters. Particle 2 has a momentum of 2 kilogram meters per second and is currently at a position of r2, but will pass 4 meters. So this distance here is 4 meters. And we want to know is what is the total angular momentum of this system about point O. Now it's worth pointing out that as long as there's no net external forces or no net external torques acting on particle 1 and particle 2, that this angular momentum of this system remains constant about point O. So that might seem odd even though R1 and R2 are changing. Now the easiest way to solve this problem, if we think of angular momentum as R cross P, is to think of it as the perpendicular distance. What is the shortest distance that these two momentums will actually these two particles will actually get to point O. You actually do a very similar process when you do torque and you do R cross F. You kind of look at what is this angle in here. So what we're going to do is find the angular momentum of each particle and do R cross P1, R2 cross P2. And basically what that means is we have this shortest distance, what we call that perpendicular distance, and multiplying that by the regular momentum. Now there's a negative sign in here because one of them has a counterclockwise angular momentum, particle 1 does, and particle 2 has a clockwise angular momentum. They have opposite directions of angular momentum. So if we actually do the math here, we get a total angular momentum of 2 kilograms meters squared per second. So there we go, we got our angular momentum of this system, and it's worth pointing out, as long as these two particles move at this constant momentum along these horizontal paths, this number doesn't change. Now the second one I have is a fun one that comes off of an AP exam. I don't remember what year it is off the top of my head, but this was a problem that was on the mechanics portion of the AP exam that stuck in my head because it's particularly interesting in terms of angular momentum. Here we have a collision, and we have a horizontal system that consists of a ball of mass 2, M2, and a uniform rod with a mass M1 and a length D. The rod is attached to a table with pivot point P at one end of the rod and is initially rotating at a constant angular velocity of omega. And it gives us the moment of inertia of the rod, and it actually tells us there's no friction in this system. So the rod strikes the ball, which is initially at rest, and after the collision, the rod is stopped, but the ball moves to the right at some constant speed v. And in terms of m1, m2, d, and omega, and any fundamental constants we can think of, we're told to determine the speed of the ball after the collision. Now, at first glance, you might say, well, collision, conservation of momentum would make sense, but we run into a problem because the rod is rotating to begin with, And so how do I deal with the momentum of the rod? Do I do momentum of the center of mass of the rod, and then how do I work that out? Well, it happens to work out that we can use conservation of angular momentum in this equation, or in this situation. And what we want to do is think about the angular momentum of this mass, or of this ball, as it moves away. So what we're going to do is angular momentum of the system initially equals angular momentum of the system final. And so the initial angular momentum of the system, I omega, there's I for the rod times omega, is equal to the momentum, or the moment of inertia of the system after the collision. And so what I've done is I've done m2 d squared, because that's the moment of inertia of this particle sitting at that point, and I've plugged in what the kind of angular velocity is the exact instant after the collision, v divided by d. You could also do a similar trick that we did in the previous problem and say, well, d is the horizontal distance, mvd, which is what I basically have here. Now here we can solve this out for v. Divide both sides by m and d, and we get v in terms of things that I'm told I can use, m1, m2, d, and omega. So really the only things that matter are these two masses, d, omega, and really the fact that we have a rod that's attached to the end. Now some of the other questions it asked us in this problem, it asked us about if this was elastic, what is the ratio between m1 and m2, which is a really fascinating question if you actually think about it. We can talk about that question later. And it also shifted, what if we move this pivot point to the center of the rod? What happens to this velocity? So this is a problem where you have something, the linear motion of m2 afterwards, that we can think of it in terms of angular momentum, and that we can use conservation of angular momentum in a problem that doesn't really seem obvious at first glance. So if you have something that's rotating and it's involved in a collision with something that's not rotating, I would maybe think angular momentum as a way to solve that problem. So let's get a quick overview of angular momentum and how angular momentum gets conserved. We'll definitely come across angular momentum again when we start to look at the motion of, or the orbital motion of planets, because angular momentum is another good way to discuss the rotational motion of planets around, well, the sun essentially.